Welcome to this video. My name is James McInerney, and in this video what I want to do is I want to take you through a little bit the software program I have been developing called panGPT. panGPT is a program that implements the next token prediction style of model that has been used quite widely in the development of large language models, and what I've done is develop this program in the hope that it's going to be useful to people that are interested in sequences. And the sequences might be sequences of genes, sequences of proteins, sequences of genomes. My own particular interest, I'm interested in the pangenome, which are multiple sequences of multiple genomes in a particular group of organisms. Nonetheless, the program, in its essence, is implementing transformer and maybe other variants of transformer like the longformer, which is in there right now. But these transformer technologies seek to answer the question, what is the next token? What is the next token that I should predict? The next word in a sentence, effectively. And how it does that is it first of all builds a language model. That is to say that it tries to understand the relationships of words to each other and also their positional encoding, or their relationships in terms of how close they should be, how far away. And that changes, of course, with context and with different kinds of sentences and so on. The idea that languages, natural languages, and genome scale languages or genome type languages might be in some ways similar, that's not a new idea. But hopefully this program can answer some questions for you about whether your data could be modeled in a way that's analogous to languages. I'm not going to say too much about large language modeling. I'll put into the comments here, I'll put some links to really great videos that explain transformer technology. I'm not going to try to do that here. I'm just going to take you through this program in a small number of minutes. Please understand I am not in any way giving you advice for what you should do with your own data. You cannot abdicate the responsibility that you have for thinking about your own data, analyzing it in your own way. This is just a tool. If it's useful, I am delighted, but I'm not going to advise you on how to do that. That said, let's get on and let's take a look at what the code is doing. And I'm not going to go into much detail. Maybe you're not interested in code, so I'm going to skip through it pretty quickly. This is the software as it is today. At the top, we've imported a bunch of libraries, and I want to say at the very, very outset that this code really is piggybacking off an enormous amount of research, code development, and so on. The PyTorch community, Hugging Face community, these have all contributed enormous amounts of knowledge, code, etc. And really all I'm doing is pulling together all of that knowledge and making it easy, I guess, for those of us in the molecular sciences to use this kind of code. So right here at the very beginning, we're just importing a bunch of libraries, a bunch of ways of doing things. For instance, this line here is importing some code that will help us to split our data set up into a training set, an evaluation set or a validation set, and a test set. And normally people do this. They train their models on maybe 80% of their data. They validate those models on about 10%. And then at the very, very end, they test the entire model on maybe 10% of the data. It's up to you how you use that, but it's all implemented here. I'm using some code from TensorBoard, which at the end will show us a little bit about the training system and whether it seems to have trained well or not. These are just some variable names. I'm logging some information so that you can see what has happened during the run, and it'll save that to a training log, and you can expect the log at the end of the training and see what it's doing. I've got some code here. This is just printing some banners, just telling you which version of the program and what it does, etc. Some disclaimers, I guess. Here we're parsing the arguments, the input arguments. These include the input file, which is the one argument that's absolutely essential. We can't run the program without having at least the input file. The rest all have defaults, and that you can change those defaults to fit your own choices. These include whether you're selecting between the transformer or longformer model type. You've got longformer specific command line arguments, numbers of heads, numbers of layers, embedding dimensions, maximum sequence length, and that's how long a sequence should we consider. The learning rate, which is how much of a jump forward you're going to make when you change your parameters. Are you going to change them by a lot or by a little as you go through the training process, and so on. The number of epochs, if you can set that. If you've got a limited amount of compute resources, you might say, look, I can just go through the data set 30 times or something like this. If you don't have a limit on how much high performance computing you have available to you, well, then you just set this to a very big number and you don't really worry about it. However, you shouldn't really train your model forever, and if it gets to the stage where it looks like it's no longer learning very, very much and the model is optimized or close to optimized, well, then you can change the learning rate so that you're taking smaller jumps right at the very beginning, maybe to really, really optimize it, maybe the initial larger jumps to get to some kind of optimum. Those are maybe too big now and you want to reduce those down. Or indeed, you've got what's called early stopping patience, which is to say that if the model really hasn't improved over, I guess in this case, the last 20 epochs, then we'll stop, okay? So we've got this kind of thing going on. You've got a maximum vocabulary size, so this is where you decide that you're going to either set this to a very big number and the vocabulary of your data is whatever it is, and you use every single word or every single token, or you can decide to reduce that vocabulary down so that rare words are not used in the training session, because maybe rare words, if they're only used once and you've got 1 million genomes involved in your training, and there's one gene in there and it's only found once, it's probably not going to tell you an awful lot about the model. So you could reduce down your amount of memory, amount of time it takes to train it by reducing your vocabulary size. Tokenizing, I'm going to talk a little bit about tokenizing. And so you save, in this case, for this particular program, we tokenize the data and we save that tokenized data to a file. What's a tokenizer? Right. So this is the very, very first thing that the program will do. Tokenizers come in all kinds of varieties. One might be for a language, for instance, you just tokenize every letter of the alphabet or every character that's used in the language, every full stop or period, every quote, every letter, every number, and they all get associated with a number. So in fact, the training is carried out on a string of numbers because the original data set is transformed or tokenized to become these numbers, these tokens. And so when we talk about next token prediction, really under the hood, it's talking about trying to predict the next number in a string of numbers. So for instance, if you've got a gene and it's called FTSZ, then that might become number 2321 in our tokenizer file. And that's because it's more standard to use these numbers, and it also gives you the freedom to tokenize in any way you want. So you can decide that in your genome, you've got 4 words. You've got A, C, G, and T, and that's it. That's the full vocabulary size. That might be, for you, it might be 20 amino acids. It might be 21 if you include X, which is the letter we use for amino acids when you haven't fully resolved what amino acid is there. I don't know how you should tokenize your data. You can break up genes into their domains and promoters. You can have introns and exons. You can just decide to go for nucleotides. You can go for pairs of nucleotides. I'm going to train a data set today. Well, not really. I'm just going to set up data set today where I've just broken down about 1 million protein sequences into words of 3, 2, and 1 letter. That's it. And just training on that might be a silly thing to do. It might be an interesting thing to do. I'm not going to say it. I'm just going to use that for demo purposes. Right. But tokenization is a whole science on its own. I'm not going to get into it today. Here we've got train size and validation size. So the training data set size, by default, it's set to 0.8. So 80% of the data will be used to train the model. The validation size is 10% of the data. So 80% plus 10% is 90%. And what's not said there is what's held back to the very end, the test set that's never going to be involved in the training. It's the test set. At the very end, we're going to evaluate the test set to see how well the model predicts the next tokens in that test set. There are things like positional encoding maximum length and dropout rates and so on. Of interest is that all of this is going to be written to a logdir, and this is part of the TensorBoard software, which will give us some insights into how the training process went. Just running quickly through some more of the data. These are the command line arguments. I'm just parsing them here because I like to do this way. You didn't have to, but it's the way I've done this. Just some code down here, set seed, printing a parameters table. So I like to see what parameters are being run before each run, and that will be saved to the training log as well. And this is just printing parameters, loading the data set. So I've got some code here for loading the data set. I've just expanded out. There we go. That's loading in the data set. Saving checkpoints. So checkpointing is very important here because, of course, this training can take a long time. You might be kicked off of your HPC system. You may not be able to train everything in one go, but it saves a checkpoint after each epoch so you can resume training, hopefully without losing too much time. So it's saving your checkpoint, loading a checkpoint if a checkpoint already exists, asking whether the checkpoint is compatible with your current run. Because subsequent runs, if you change the number of heads or if you change some parameter, then the checkpoint is no longer compatible with this new run. And so that checkpoint can't be used. The checkpoint can only be used in runs that are compatible with one another. This is the main training loop here. For training the model, we calculate metrics like accuracy, precision, F1, Cohen's kappa, that sort of thing. Validating the model, so it's slightly different when you validate the model compared to training the model. Most of the code is the same, but this line here and a few other things are a bit different. This is just some way of processing the genomes, where we've got tokenization going on up here, measuring the vocabulary size, logging some info. This is your tokenization going on here. Training size, positional encoding. I've got some SASs down here. There's a positional encoding class here for that idea, as I said, that the model does two main things. One is for every word. In our case here, it'll be a triplet of amino acids. But for every chunk of the vocabulary, what is the attention that that chunk will get from all of the other words in that vocabulary? And then also the positional encoding is to try to evaluate how nearby or far away those chunks are when they influence this particular word. Positional encoding, this is the transformer model class here. This is the longformer model class here. Transformers and longformers. Longformer is specifically supposed to be much better generating models that take into account attention that is given to a word from very, very far away. It doesn't do all of the compute that the simple transformer model does, and from that perspective it should be faster to evaluate very, very long sequences. And I thought that might be interesting for the kinds of data that we look at. I guess in the English language, quite often a sentence itself isn't terribly long, though I guess a book is. For us, a genome is quite a long sequence. So it's there. If it's useful, that would be very interesting to know about. This is the genome dataset class, just tells us a little bit about the genomes. We've got an early stopping class because that's going to be important for us occasionally. Just here's selecting between transformer and longformer, early stopping code, training the dataset, validating the dataset. We've got some criteria for evaluating what's called loss. And loss is a measure, if you like, of how well the model now predicts the next token. Those loss values are typically very high in the beginning. It's not very good at predicting, but they should improve over time. If they don't improve over time, then you've got a data set that shouldn't be modeled in this way, I guess. Just printing a lot of output, saving things to the log files. Down here, we're about to start stopping. First of all, we're going to try to reduce the learning rate. If the learning rate is not improving, then we reduce the learning rate itself so that we're taking smaller steps, and maybe that might help us. But if that doesn't happen, then after a while, you'll probably just stop the process anyway because you've decided it's not learning anymore. And down at the end, we've got the test genomes, that 10% that were never, ever, ever involved in the training. I'm now going to swap over to the terminal here where I'm going to do a little bit of a demonstration of how the software works. So I've got in my directory here on a HPC system, I've got panGPT.py, which is the Python program I've just taken you through. I've got a data set called input.prod. So I'm just going to take a look at the input data set. And as I said, it really is just a very lazy thing that I've done. I've taken about 1 million protein sequences and I've just broken them up into words of 3. If they're not divisible by 3, then you might see 1 or 2 hanging out here at the end. So there's a word of length 2, there's a word of length 1. In this data set, there are a bunch of X's. So it's not 20 amino acids, it's 21 amino acids in the data set. I think almost every 3-letter word is represented in this data set. I think literally every 2-letter word and every single amino acid is represented as well. So something north of 9,000 words, that's going to be the vocabulary size here. 9,000 is 21 multiplied by 21 multiplied by 21 plus 21 multiplied by 21 plus 21, if that makes sense. So if you start the program and don't give it any command line parameters at all, it's going to give you a little bit of a complaint and tell you, that's not enough. So just a little bit of a header here, what's happening. And then it says, this is the usage, buddy. That's the usage there. And there is one command line argument that is absolutely required. It will not run without it. And that's an input file. So if you just give it an input file, in this case, we have our proteins, our protein data set. It's already started a training log, but the input.prot, if I just give it that, then it'll just use all of the defaults and just run it. And that would be using the transformer model type. I can't remember exactly the number of heads by default in this version of the program. I do apologize. I changed the program a lot. Will be, I think, probably either 4 or 8. Embed dimensions, 256 maybe. Maximum sequence length, 256. Number of layers, probably 4, something like this. So I'm just going to run it with no changed parameters, and we'll take a look at what it looks like. So Python, panGPT, input, file, input.prot, and let's just see how it runs. So just hit return there, and the first thing it does is it gives you sort of this header, and then it gives you these parameters. This is what's running. The input file is input.prot. It's a transformer. 256 dimensions is the embed dimensions. I might talk about that in another video, what that actually means. I think it's a very cool idea. Number of heads, number of layers, and maximum sequence length. So I would say that up around here is the really important information that really sort of says what's the kind of model that you're really running. After that, then, the batch size has got to do with training the model, how big the batch is that it learns on. It doesn't learn on the full data set because that's going to be a bit of a memory hog and a CPU hog. So it learns in batches and then aggregates these batches together. The model dropout rate, when it's training, it deletes some nodes. So in this case, it deletes 1 and 5 nodes. And that helps to prevent overfitting when you're training up a model like this. Let me see, what else is there? Just the learning rate patience. If the learning is not improving, if the loss rate is not reducing, then at some point, and here after 10 epochs, it'll just reduce the amount of change that's introduced per epoch to see if we can optimize in that sort of way. And if not, then after 20 epochs where it's not really learning anything new, it's just going to stop training, and then it's just going to save the best model that it ever found during the whole training set. Not the last model, but the best one, probably 20 models ago. Let me see. I've set the maximum vocabulary size to be a very large number. We'll talk about that in a while. Models check path, the tokenizer file, where 80% of the data has been used for training, 10% for validation, which means 10% of the data is there for testing at the very, very end. The seed number is of course 42. I hope you can understand the reference to that. The positional encoding maximum length is 5,000 tokens away, dropout rate, and the logs directory is this. The data set that we loaded was a total of 956,589 sequences. The lengths are, the minimum one is 85 words in length, 85 tokens, and the max is 9,630, and the average is 430. And the pre-processing the sequences has gone ahead. The total number of trainable parameters is 9.9 million trainable parameters. That's a very small model. The Llama model that was released recently was an 8 billion parameter model, so that's 8,000 million. This is 9.9 million, so much smaller than that sort of thing. It didn't find a checkpoint because this is not restarting from a previous training session. So starting from scratch, the vocabulary size is 9,182 words. Embed dimensions 256, number of heads is 8, number of layers is 4, and the maximum sequence length is 256. So it's really just thinking about a window of 256 when it's thinking about positional encoding and thinking about the relationship of triplets of amino acids to each other. So it's training away here. It's going through epoch 0. It's about 19% through in the training, 20%. It's broken it up into batches, and the batch size is 32 sequences. So for our million sequences, that's really 23,915 batches it's going to train on. So it's optimizing within a batch. It's optimizing numbers. These batches are relatively small. Relatively small batches are good because it can help to prevent overfitting, but it might slow things down a little bit, and maybe batch size of 32 might be a bit small. I've got enough memory on this system, I could probably have increased that a little bit. It's ripping through 25 batches per second, more or less. And this is a little countdown clock here. It's been running for about 4 minutes. It's got 11 minutes left, that sort of thing. Now, as you can see, it's probably going to run through 30, 50, 100 epochs. It's going to take about 15 minutes per epoch, so that could be quite a long time. We're probably not going to sit here and wait for that right now. What's going to happen as this goes through is it's going to print to a file some logs. It's going to print to screen what these logs are, but like many good cookery shows, I've done some of this already. And what I've done is, this is the directory online on our ADA system, our HPC system. This is where it's running, but I've also downloaded some logs from earlier, and we're just going to take a look at those logs now. And this is the result of a training run. In here, I've got this logs file. And this is what they look like. They've got some information about the system that it ran on, etc. So now we're going to take a look at this log file. And I'm on my desktop machine because it's easier for me to take a look at these logs. I've just pulled them down to my desktop. What I need to do is I need to run the program TensorBoard and just tell it where the log dir is, the log directory in its logs. Hit return. It's now processing these logs. And what it's going to do is it's going to say to me, I need to take a look at localhost at port 6006. And so I'm leaving TensorBoard run, and I'm going to swap over, and I'm going to paste in the URL. This is what the logs look like. I'm just going to close up all these windows for us. So we have logged the accuracy, F1, Cohen's kappa, learning rate, the loss, perplexity, precision, and recall. First, I would want to take a look at the loss, because the loss values will tell me whether the model got better at predicting the next token over the course of the training period. So this is loss from the training, and at the end of every training epoch, we take a look at some validation data to see how well it does on data that wasn't used for the training. And what you can see in both cases here is that the loss reduced over the 20 epochs the training period was run for. Now, I'm not saying 20 is the right number to run these for, but that's what we did in this particular case. And it still looks like there was lots of room to go, and it should run for longer. This is the training set. Started off a loss value of 2.4, and over the period of 20 epochs, it reduced down to a loss value of something like 1.31. The validation set started off as well pretty high. It wasn't good at predicting the validation set, at 1.8, and eventually ended up with 0.82. In our case, the validation dataset had a lower loss value than the training dataset, which might seem like it's a little bit unusual. But for the training set, we have certain dropout of nodes as we train, and it's very, very likely that's the reason why you have greater loss in the training set than in the validation set, because we have this dropout rate to prevent overfitting and, in fact, just memorizing the training set rather than actually learning the features of the data. Nonetheless, it seems to have learned something over time. Whether that's actually useful to you or not, I do not know. We have accuracy, recall, precision, F1, and Cohen's kappa. These are all the metrics that the program will produce right now. And this one here is the accuracy metrics. It's kind of the overall ensemble of false positives and false negatives and how well the model did overall. I think people quite like taking a look at the accuracy rate. So in the beginning, in terms of accuracy, it had a value of about 0.72, so reasonably accurate even in the beginning. But at the end, then its value was closer to 0.9, 0.89. Was the accuracy value. So that is the program. I'm just swapping back here so that you can see it's still training away. It still hasn't finished its first epoch, and it won't finish for another few minutes. If you like this video, please subscribe to the channel. If you have got any questions, please leave them in the comments. I am a one-man band right now. I cannot guarantee that I can get back to you on comments. I work on this myself, and it's something that I do in between all of the other jobs that I do. So I will do my best to come back to you, but if you liked this video, please give it a thumbs up, subscribe to the channel, leave a comment, and I'd be more than happy to hear what you think. Thank you very much.